This is the Daily Space for today, Friday, June 19th, Juneteenth, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Astronomy can be described in many ways: awe-inspiring, mind-blowing, complicated. There are so many adjectives to pick from that sometimes just calling it astronomical is really the safest bet. Today, though, our science comes with one clear option. It's pretty. The team behind the E-Rosetta X-ray telescope aboard the Russian-German Spectrum-Roentgen Gamma telescope have released their first all-sky survey. This amazing data set looks at the X-ray sky in higher resolution and with greater sensitivity than has ever been observed, going 4 times deeper than the Rosat mission's all-sky map many decades ago. This is the first data release from this mission, and it represents only the beginning of what this mission will produce. During the next 3.5 years, this spacecraft is scheduled to complete 7 survey mappings of the entire sky that, when combined, will give us 5 times the sensitivity of this first survey. The X-ray sky looks very different from what we're used to seeing with our optical telescopes and eyes. By combining data from more than 400 million photons with X-ray energies between 0.2 and 8 kiloelectron volts, the team behind the survey has built amazing color images of our high-energy sky that allow us to clearly see these differences. The center of our galaxy appears not as a blob of stars, but instead as the center of an hourglass. The 2 bulbs of the hourglass are Fermi bubbles, bubbles of material that were pushed out and shocked by the energetic feeding of our galaxy's supermassive black hole at some point in the past. Scattered through the sky are blobs and knots of bright light with supernova remnants and the nearest star-forming regions and even galaxy clusters. Publications of surveys like this enable future research that can statistically analyze how common different kinds of objects may be and to understand the systematics of our universe. In general, surveys don't feature a lot of results. I can tell you this survey is estimated to contain 1.1 million sources that are mostly active galaxies, as well as some stars with strong magnetically active hot coronae. While of enormous scientific interest, galaxy clusters, they're only 2% of the sources. And the fraction of the sources that are associated with X-ray binaries, supernova remnants, and star-forming regions is an even smaller fraction. The survey image and all other images that are going to be discussed during this show will all be available on our website, dailyspace.org. For now, I'd like to keep highlighting some of the cool things in this particular X-ray survey. The team showcased several key features in their data. One of the most stunning is their imagery of the triple nebula, Vela, Vela Junior, and Puppis. These 3 supernovae remnants vary in age and distance, with Vela and Puppis A containing pulsars, and taken together, they give us a singular perspective on this kind of an object. While less spectacular, my favorite image in their data is the light echo of a transient X-ray source. At some point in the past, X-ray binary MAXI J1348-630 went into an outburst and erupted with X-ray light. While some of that light traveled straight toward us, most of it went off in every other possible direction. Now, some of that other light has scattered off of surrounding material and has made its way toward us thanks to that bounce. We see that scattered light as a spectacular little ring around the binary. Now, while Chandra has produced a lot of stunning X-ray images over the years, this is the first time we've had an X-ray survey capable of this kind of stunning data collection. This is the entire sky at this level of detail. Now, most telescopes aren't survey telescopes, but every facility was built with a certain purpose in mind. One of the oft forgotten purposes of the Hubble Space Telescope was to, well, help us understand planetary nebulae. Now, more than 30 years after its launch, HST is still struggling to fulfill this goal that it started working on back in the 90s. When stars approach the ends of their lives, they shed their outer layers. This material drifts away, creating a myriad of complex shapes that appear as round or roundish blobs in most Earth-based telescopes. With Hubble, these blobs get resolved into complex shock waves and trendles of material. And even back in 1997, it was apparent that these nebulae don't have a one-size-fits-all explanation of their structures. Today, using the third edition of the Wide Field camera, astronomers have shown that the level of detail and nuance seen in these objects only goes up as observations get better. Using the full observational range of Hubble, observing from the ultraviolet all the way out to the infrared, researchers have looked at two previously studied nebula, NGC 6304, or the Butterfly Nebula, and NGC 7027, which is the Jewel Bug Nebula. The two bizarrely shaped nebula are thought to be the result of binary systems, with the orbital plane of the two systems pinched in the waist of the expanding material to create an hourglass. The different colors in these images each trace different atoms and temperature ranges. The image's high resolutions allow individual shock waves to be studied, revealing in the process that both systems underwent rapid fluctuations. In fact, the researchers can even measure some differences between these latest images, which appear pastel in color thanks to the ultraviolet getting colored into the blues. And when they compare these images to Hubble's early data, which appears quite red. Now, ultimately, researchers hope to sort the details behind how the structures in these planetary nebulae formed. It's nice to say these are binary systems, but that lacks specifics. There are currently two competing theories for planetary nebula formation in these complex cases. Either two stars orbit one another and interact such that they create a disk, which in turn generates the outflowing material, or the two stars merge and the merged object is outflowing jets. According to team member Bruce Ballack, the hypothesis of merging stars seems the best and simplest explanation for the features seen in most active and symmetric planetary nebulas. It's a powerful unifying concept, so far without rival. While astronomers continue to study this problem, we can continue to expect more amazing imagery. I have to admit, it almost makes me hope that it takes them a long time and a lot more nebulae to figure out all the answers they want. Now, our final story of the day has no pretty pictures, but it does come with a pretty illustration. Folks studying planetary formation have been struggling with, well, just about everything. Back before we had good data, some models suggested that planets might form in a few 100,000 years once the process got started. We were a little shaky on when it might get started. And then we started seeing disks around stars that are 1 to 3 million years old, and things looked good for forming planets. Until we realized those disks don't have enough stuff in them, enough dust to form planets. And this raised the question of what's going on. We know there's planets out there. It turns out that the disks we've been looking at are likely post-planet formation and are in many cases only showing us what is left behind. In a new paper in Astronomy and Astrophysics, a team of Dutch researchers described new observations of protostars still forming in the Perseus molecular cloud. And they found that the conditions in these exceedingly young systems are perfect for planet formation. This means that before a star fully settles into nuclear burning, it already may have planets surrounding it. So yes, planets can form in a few 100,000 years, and it may be the first few 100,000 years or so when that formation takes place. It's a wild universe out there, and our understanding keeps changing, and we're going to keep bringing it to you as it does. For now, though, this is all the science we have for today. Thanks for being here. This has been The Daily Space.